Baker's Trust name in derivatives at the time. It's since disappeared. It was acquired by Deutsche Bank, but it's a very prestigious position he had. And so he co-founded Risk Capital, a successful independent risk management consulting firm, which was sold in 2006. Since that time, he's combined private consulting with entrepreneurial ventures and asset management and credit. His current research focuses on advanced valuation techniques, such as the application of derivative pricing technology to corporate assets, liabilities, and decisions. I should also mention that he wrote a book a long time ago, which everyone refers to as the Little Green Book, and it was a really nice introduction to continuous time finance, which is the title actually of the book. And so it's kind of a classic. And so if you can get your hands on it, and it's probably in my library there, you should take a look at it. Okay, David, the floor is yours.
Well, thank you for the kind introduction, Peter. I'm sorry that you seem to have got the long version of the bio. It's ironic that coming to NYU, I think the best thing about it for me as a former academic was to really come back to my roots and try to work with students such as yourselves to teach finance in a logical, interesting way. And also with enough of an eye on practice to make sure that it was relevant to you. So when Peter mentioned I wrote this book on stochastic calculus, what I'm going to do today is basically tear up the book. Because I'm going to try to convince you that you don't need to know stochastic calculus in order to price options. And in fact, it's really going to be relatively simple. It's going to be so simple, in fact, that I've actually prepared a second presentation because I'm worried that you're going to understand the first one so quickly that I'm going to have something to say for the rest of the time. So if that happens, then I think that might be fun to actually see a presentation. My second presentation, if we get to it, is called The Most Beautiful Equation in Finance. Taking off on the physics and the mathematics versions of that and having a version for finance. And I hope to persuade you that our students here at Tandon are studying the most beautiful equation in finance in their valuation class. As you can see a few examples of the kind of work that they do. Okay, I tried to pick the simplest title for the simplest talk. So here it is, simpler option pricing. Now we need simple, where's the guy who's supposed to be here till slide 2?
Yeah, exactly. Okay. This time we're ready for it. Yeah.
All right.
Did you see how we did that?
How did you do that?
No, just try going back one more. Go back. We didn't have to click on it.
Okay. I did click. Anyway, if you took my class like when I taught at USC, you would have seen this. And everyone, I think, here in this room, especially the practitioners, have probably seen this already. And people do this in the back of napkins to practice and stuff like this on the bus. I see it all the time. But the derivation of the option pricing formula is not simple, right? You need stochastic calculus, and you should know these steps, right? You have your stochastic differential equation for the stock price. You find the call option price, which is a continuous function thereof. You find the stochastic differential equation for the call. You make this hedge portfolio where you combine the call together with a certain number of shares of stock. And here's where the magic happens, is you take the differential of this, and even though the hedge ratio is a function of the stock price, that somehow disappears here through an assumption called self-finance, which we're going to come back to today, okay? So then you make this portfolio risk-free. You say it has to earn the risk-free rate of return, therefore, and you get a differential equation where it just so happens that the risk premium vanishes from the equation. Then you solve this differential equation with the boundary condition, and you get the famous Black-Scholes European option value. Okay, and I think anyone who's in this field who's done this could do the same pitch I just did. Let's see now a different alternative way. So my first claim today is I can derive both the Bachelier and the Black-Scholes-Merton models without stochastic calculus. All we're going to need is a little bit of differentiation. And maybe we'll look up a few integrals in the table. We won't even actually integrate ourselves. The second comment I'm going to make is that academics have tried to use simplified versions of the CAPM, for example, to value options. It's been a disaster. And some of the papers that have been written are called things like option pricing is a disaster when you try to use the CAPM to do it. So it was really kind of ignored as an approach for valuing options. What I'm going to propose is a solution to the problem that plagued these authors many years ago. How to get around the problem and fix it today for you, to show you that all we have to do is make one assumption. We're going to add this to the CAPM, and all of our problems are going to disappear in the pricing. And the assumption is called convexity. Now, I know, again, the professionals here will know what that means, that the options prices have to be convex in the strike price. In case you don't know, I put a diagram on the whiteboard here, which says that if you construct a strategy, right, we buy a call option at one strike price, then you move up a little increment delta and sell two call options at that strike price, and then you go up another little increment delta and buy one call option back. That strategy is called a butterfly spread. And you can see it always has a positive payout. Because it always has a positive payout, it has to have a positive value. The last step is then you make that little delta shrink like a little differential. And the limit to that expression, you can see that pattern 1 minus 2, 1. It's just the numerical second derivative, right, of the call with respect to the strike. And so that is going to approach the continuous derivative. So this is my condition, is that the second derivative of the call with respect to the strike has to be 0 or positive. Just can't be negative. That's the only thing we require. When you make that assumption, everything goes away. So unfortunately, when you use the CAPM to price these options, you get both non-convex prices. You also get negative prices for the options. So I like to think that the convexity condition means that I can eliminate free lunch for traders. If I can get rid of the negativity problem, I can also get them free dinner. Okay, after we add that constraint, it's actually very easy to derive the model. So that's the talk, really. Here's the notation. We have an asset, its value is V. Its unknown future value is a random variable M. And VC is the call price. Each one has a mean and a standard deviation. There's no risk neutrality. This is all in the natural measure, okay? So it means and standard deviations, and we have strangely enough, we have a covariance in an option pricing model. Might be a little bit surprised to see that. And of course, you can calculate a regression beta because you have a covariance and a variance. This is all discrete time modeling, where it's just 2 periods, time 0 and time 1. And I'm going to value the option first for the Bachelier model, then for Black-Scholes, using this notation, these assumptions. There's a price of a risk, which is called A risk aversion coefficient. Risk-free rate. B is just a shortcut for the present value of a 0 coupon bond. And X, of course, is the strike price of the option. I think it'll be pretty clear. So in the CAPM, what happens is when you value the market portfolio in the CAPM, for example, we start with options on the market to make this simple. We can say, all right, if the market portfolio has a future mean, the way to value it in the CAPM is to subtract the cost of risk times the amount of risk as measured by the variance of the market portfolio. This is why the market portfolio has a market risk premium. And once we do that, we have a certainty equivalent, which we discount at the risk-free rate to find the present value. So that's for like the market portfolio. And you don't technically even need to do this, but it's really helpful to me. I'll show you why in a second. This is the really important one. How do you price an asset that's in a portfolio in the CAPM? Is you say, all right, I'm going to take the mean. I'm going to subtract the risk charge multiplied by the covariance. And then I have a risk neutral equivalent or certainty equivalent, and I discount that at the risk-free rate. So this is the value of the derivative, in this case, the option. Now, the reason I did the A in both cases, I priced both of these with risk aversion in them, is so that I can take the two equations, put them together, eliminate A. And when I do that, I get a very nice looking formula, which says the value of the call option is equal to the value of the stock times some factor beta, plus this constant times the value of the 0 coupon bond. Just a simple regression. And to illustrate what the regression is, take a look on the right-hand side here. We have the payoff of the stock and maturities on the x-axis and the call on the y-axis. And of course, the call option is going to have this hockey stick payoff. But if you draw a regression line in here, you can see this is exactly what we're doing. We're going to price the call relative to the stock and the 0 coupon bond, which is like the intercept portion. So it's no surprise then that the slope looks like beta. The intercept is in fact this term, right? The mean of y minus beta times the mean of x. So what the CAPM really gives us is a kind of a simple way to value assets using regression, projecting the value of the option onto a stock and a zero coupon bond. Okay, so far? It's hard to tell with the masks on sometimes.
Well, quick comment. I mean, a one-factor model where the one factor need not be the market portfolio would go this far as well.
Absolutely. In fact, I'm being quite lazy saying to use the CAPM because it's really a much looser restriction.
Okay.
Right? Any model that leads me to covariance pricing will work.
Okay.
And I can also say this doesn't have to be the market portfolio. I can think of the portfolio as being the stock and the call, right? I'm pricing the call in the context of the portfolio, so I need covariance pricing. It's funny though, when I talk to financial engineers, a lot of them don't have a lot of practice with the CAPM. They know all the engineering math very well, but they don't necessarily know the finance stuff, which is, it's so simple because it's all based on normal distributions and all these idealized assumptions like constant parameters. Okay, so if you were valuing this option, you could say, look at maturity at this regression and say, all right, I have an intercept and I have a slope, right? Call is a function of the stock price. I can discount the intercept at the risk-free rate because it's just a constant. So that's my zero coupon bond. The slope at time t, when I bring it back to the present, I just use the price of the stock today. So effectively, I split the option into two components, right? The zero coupon bond and the stock. There's no doubt about what the discount rate is because this part is discounted at the risk-free rate. This part is discounted at the rate of return of the stock. Okay, so I'm just projecting on those two assets. Now, it might not be a very good fit, but it can still be a good valuation. If that's the best comparables you have to build that valuation, then you're going to get, that's your best outcome. So the slope, of course, is equal to the covariance between the call and the stock at maturity, divided by the variance, and the intercept, like always, expected value of y minus the slope times the expected value of x. Okay, first option. The Bachelier model is characterized by the assumption that the underlying asset follows a normal distribution at maturity, which is great because now it's going to fit very nicely into these market models, right? Or these CAPMs where you assume that things are normally distributed. Okay, so Bachelier model, one period, discrete discounting, no dividends, and asset price is normally distributed. So it's going to be really nice, beautiful, perfect model for us. So we calculate the expected value of the call at maturity. So this actually is, if you look up truncated normal distributions in Wikipedia, you can find this very easily. Right? It almost looks like an option pricing formula, right? You take the mean of the stock minus the strike price multiplied by this cumulative normal distribution factor, right? Plus this adjustment. Okay. It almost looks like an option pricing formula already, right? It looks like we could almost go home. And that's really the secret here, is most of the juice is in knowing what the mean of the truncated distribution is. Here's the next fun thing. I need to know the covariance between the call and the stock at maturity. So the covariance between the stock and the call payout actually turns out to be sigma squared times n of d. Okay. So if you don't see it right away, you realize that these are perfectly correlated whenever m is greater than x. Otherwise, they're perfectly uncorrelated. If you integrate all over all those possibilities, you're getting an n of d multiplied by sigma squared. You told me the name of that rule. What was it?
What?
You told me the name of that rule, didn't you? Remember? Stein's lemma. That's right.
Yeah.
Okay, so our beta then is n of d, the cumulative normal over this d value, and d is how far away we are from the strike price in standard deviations. So now this looks very much like the Bachelier formula. We make these substitutions with the covariance and with the expected value, and we get something that looks like Bachelier, but it's not. What's missing? We know secretly that it's wrong because it's not risk neutral. Everything was done using the natural distribution of these variables. So what happens is when we try to use this model, it fails. And that's why, all these authors that have written about this subject have been very frustrated with using the CAPM to price options. Because what happens is you get a call option as a function of the strike price, which instead of being a nice like dotted gray line here, like it should be, actually looks like this dashed blue line. And you can see two problems with it, right? It goes negative, of course, but also it goes non-convex. Right? And the put doesn't look so bad at first, but then when you take a closer look up at the top, you can also see it becomes non-convex. So what if you were working in a market, and I like to think of the gold market because it's something I know something about, right? And if it was trading in a free market and suddenly some country announces they're going to pay a certain price for gold, what's going to happen? It's going to automatically go to that price, right? This is going to have a support or a ceiling. So it's going to go to that price as it acting like a constraint on the equilibrium prices. So that's what I'm going to do here. I'm going to constrain the prices that I get from this valuation. Okay, and you know what the constraint's going to be? The convexity constraint, because as Merton showed us, option prices have to be convex in the strike. So I'm going to take the same old CAPM market model, add these two assumptions. One is you can get calls for any strike price, and second, you're not allowed any static arbitrage opportunities. There's no continuous time here. It's just now in time one, right? And there's our requirement. The second derivative is positive. Not bad, right? When you do that, here's the magic. And I hope you won't mind when I explained this to Peter, he said, wow, the first time, because it kind of just jumps out at you. But when you calculate the second derivative, I put the 1 plus r on this side just to make this a little neater. Here you get this expression, which is the product of the normal density, right, with standard deviation sigma, times this term. Now, what does this say? This is 1, so that's just recovering this, plus d over sigma. D is, remember, that's x minus mu over sigma. So this can be any sign because x can be any sign. It can be positive or negative. This is, what is this? This is the risk premium on the underlying asset. So if you take the underlying asset's current value and you gross it up at the risk-free rate, the difference between that and the mean is the risk premium for that asset. So you look at this equation and say, how can I force this to be always greater than or equal to 0? And there's only one way, maybe two. I could make sigma infinite, but the easier way would be to make the risk premium 0. Okay. So it's not exactly a proof. I don't think. There's something about it that still bothers me, but it's within this class of normal distributions, it's definitely the case. This could be the only pricing model. Unless you could invent some other way to make this go to 0. Okay, so that's it. When you make this substitution, this is the risk neutral substitution. We replace mu wherever we see it with the current asset value times 1 plus r. Then we get exactly the same equation back, but I'm indicating now that it's d star, right? Because now instead of x minus mu over sigma, it's 1 plus r times v minus x over sigma.
Remember that one?
Yeah.
So my thought was make mu depend on d in such a way that the product of t and what's in brackets is positive. Is that clear what I'm saying?
Yeah. So that's what I'm saying. That's why it's not a proof. Because you can come up with like these crazy things that could work, that could cause this to be positive.
Admittedly, that's great. I mean, I agree with your statement.
Right?
So this, at first glance, it sounds crazy making u equal b 1 plus r. Let's say, like they're both. Let's say, I mean, it's hard to look at things from a fresh set of eyes, but
that's the biggest challenge in this project, to be honest, because if you know what the answer is, you're wondering, did I prove it or did I, repeat it?
Yeah, because let's say, like, if you make mu equal v1 plus r, it does accomplish a goal. But let's say, you can imagine the reaction of somebody who thinks that all assets with risk must carry a positive risk premium, as opposed to.
Yeah.
Okay. Yeah. Okay.
Absolutely right. So you made the substitution, everything works right. And you get back the option prices, these ones, the dotted gray and the dotted yellow, which make perfect sense, what they should be. Okay. Now I'm going to say a few things which I think are a little provocative. What if I took my wrong pricing formula and I just said, why don't I just take the derivative with respect to mu and set that equal to 0? Somehow I choose that. Then I could get this right away. I'm doing it on purpose. I'm enforcing risk neutrality, basically, right? You would say that's ridiculous, right? Going back to your standard of going back in time and saying we're going to impose risk neutrality, people would think that we're crazy. But nevertheless, I could do this, right? It corrects my CAPM problem as well. Guess what? I just, for the fun of it, I took the self-financing condition from Black-Scholes, the continuous model. And I calculated out the terms that had to be equal to 0. And I get this equation here, this differential. Taking the derivative with respect to mu, I find I get exactly these two conditions. When I make this substitution, that the value has to be the risk neutral mean discount the risk-free rate. The beta, the hedge ratio, has to be the partial of the mean of the call with respect to the mean of the stock, evaluated at the risk neutral stock price. This assumption is like a sledgehammer. The self-financing assumption forces the same thing as making the derivative of the call with respect to mu equal to 0. And what's worse is I can't even define it because it's a discrete model. What does self-financing mean in a discrete model? So there's something about this equation that's causing this to happen. Anyway, so now I'm going to do Black-Scholes. And this will go very fast because now you have an understanding for Bachelier. But before I do, I'm going to make a little bit of a rant. Because I was never crazy about Black-Scholes. In fact, being in the commodities business, most of my clients were using Bachelier models or other models for option pricing, not Black-Scholes. Good thing because we had negative oil futures prices last year, right? So my rant is, why is Black-Scholes so relevant to us? Well, first of all, stock prices can't be negative. I can't fight that too much. But we do make a big deal out of it, especially for large stocks. Most importantly, though, stocks cannot be 0 in the Black-Scholes model. And we know plenty of times stocks get to 0. If you have a low price stock with a high volatility, you can't make that thing go to 0 no matter what you do in Black-Scholes, right? And finally, of course, we all know that the positively skewed log normal distribution of stock prices does not fit the data at all. And so we fix it by allowing a constant in the model, implied volatility, to absorb all the shock, right, in the pricing. Okay, so even in spite of this, I'm going to proceed, but I just want to have my complaints on the record. And now we're on YouTube for everybody to see, right, Peter? Yeah. So let's do Black-Scholes anyway. So we'll calculate the mean. S0 is going to grow at a rate of alpha. The risk premium for the stock is what you get if you get the expected value minus what you get if you invest the risk-free rate. The mean is a little more complicated, right? But it looks very much like the Black-Scholes model already, right? That's just the expected value of the option payout. D1 looks a little more complicated because this is a log normally distributed variable, but that's not a major issue. I did retain the alpha to remind myself that these are the natural distribution, not the risk neutral distributions. So whenever you see an alpha, that means it's the natural distribution. So if this is the stock risk premium, the option risk premium in the CAPM is just a fraction of that. The beta turns out it's a little bit different here because it's the like the static hedge ratio in Black-Scholes model. So you can calculate this analytically, by the way. You can calculate the analytical covariance and variance of these of the two distributions. And here's what you get. Looks kind of like Black-Scholes, except for the alpha business, and then this risk premium at the end. But what are we going to do? We have the same problems once again. This time I'm showing you the probability distributions are dipping negative. It's not going to work. Gotta give it up. Or put a constraint on the model, force the convexity condition. You notice I was able to just copy the slide from before. Right? Isn't that a nice cheap trick? Calculate the second derivative. And what do you get? It looks qualitatively similar. This is the log normal density multiplied by 1 plus this term, which is the moneyness, divided by the variance of the stock, times the risk premium in dollars for the underlying. Turns out nicely, right? And you ask yourself the question, can this be negative? And I just demonstrated in the last slide that it could. All it takes is one example, right? So how do I fix that? The problem is the moneyness thing can be positive or negative. This is positive. This is probably positive, right? If alpha is greater than R. At least it's a single sign. This is going to be positive, well-behaved density. So all our trouble is coming from the moneyness. So the only way, without contorting our constants and turning them into functions, is going to be to force this to be 0 by forcing the risk premium to be 0. That's it. When you do that, you get the European call. And you have alpha R instead of alpha. So 1, 2, 3, 2, 4 pages, right? Isn't that easier than the Black-Scholes that we teach? No differential equations. I didn't really use integrals. I used a few, but they were integrals that people knew about already. And I just took some derivatives. So which one do you prefer? Black-Scholes-Merton development?
The funny thing is, I think Black would have preferred yours to his own model. That was really true. He was like, you read his background. He was totally against, what you were calling Black-Scholes-Merton there, fairly.
Yeah.
Yeah. So
I had the same thing. I read his biography. I said, well, this guy is really like intuitive guy. His contributions go far beyond the published research. Okay, so it's your choice, simple option pricing or this sort of stochastic calculus. Now, I think Black-Scholes, personally, the power of Black-Scholes is that it taught us risk neutrality. And that was a great thing. But the derivation itself, and I think I've remarked this to you before, I think that Black-Scholes, they kind of jumped 10 steps ahead of everybody at that time. And maybe we didn't need that much power to be able to get the results we needed to do these kind of relatively simple option valuations. Okay, any questions? Yes. So the question is what to optimize in order to construct the Lagrangian. I did experiment with various things and I couldn't make that work myself. It doesn't mean it doesn't exist, but I didn't find the right objective function to make that work. But it's a nice suggestion.
This is maybe a slightly different direction than what you did. I know you just trying to come up with simpler option formulas. But one thing that occurs to me is this is kind of, I think, again, I'm vague on I'm like instead of financial engineers, but my understanding is you're kind of penalizing based on variance effectively, and because it follows from mean variance. And for options, given like the calls in particular, given that the upside is really where the value is, I think penalizing based on variance, it doesn't make sense. So I'm curious if you're aware of any work where somebody uses increasing utility functions to find a value option that might be something similar.
I think it's a good idea. I mean, the fact that the option return is not normally distributed means it doesn't really fully fit the CAPM model. But it's also the case for the Black-Scholes derivation we did, it doesn't fit the CAPM either because of the log normal underlying assumption. So I guess what happens is the linearity is getting us close in both cases. And then we're using this, the convexity constraint to find that nonlinearity correction.
Right, because one of the things I noticed when you showed this chart at the first attempt about your convexity constraint is that the call prices were below like the model call prices and the put prices were above.
Yeah.
Which is indicative of penalizing for variance.
Yeah,
penalizing the upside.
that's a very good point. Very good point. Thank you. Okay.
Do you need that second derivative exists in any case, or it's enough that at the butterflies can exist without any limit of that kind, so that the density in some points could not exist, for example.
So do you mean not exist or zero?
Be zero or
Yeah.
He means that the function, the call pricing function is convex, but not twice differentiable.
Right.
Yeah.
So I think this would be, if I were doing this in a more general way, I would allow this to be zero in places where it was impossible for the stock to reach those points. Yeah, absolutely.
so this is the same condition that this peacocks that this refers on productions and peacocks have and how is condition to be is quite restricted because it requires a continuous distribution.
Yeah, I'm still in the world of continuous distributions and, and trying to build up a kind of, it's more of a pedagogy. Yeah.
For binomial tree.
Yeah.
In which this condition you cannot go beyond the condition of the boundary.
That's right. So this method wouldn't work for that. Yeah. Yes.
So CFPM, the price and return are the endogenous variables in CFPM.
The price of the
The price and return are the endogenous
endogenous, okay.
variables in CFPM, but we are assuming the underlying is distribution. So would that underlying contradict to the CFPM framework?
Yeah. So when we talked in class today, we took the cash flows to be normally distributed. So if you look at that version of the CAPM, I think it would be easier to understand what we did. And just like we did covariance pricing today in class, this is why I was excited for the class to attend, so that you could see that it applies to the option as well as to the stocks in the portfolio in the CAPM. Yeah, thank you. Okay, so I threatened a second presentation. So I think I'm going to carry through on my threat. Can you help me change it, please? And now the magic show begins. Can we turn down the lights, have some sparkles? Where's our AV people when we need them? Okay, so I'm competing, and I already have some heavy competition because Peter Carr has told me that he thinks the best equation in finance is P&L equals infinity. And it's hard to argue that. I mean, that's a pretty good equation, right? Infeasible as it may be. So I'm trying to follow in the tradition of Feynman in physics and I don't know who in mathematics, trying to define the best function in those fields. And that hopefully as financial engineers, we can find our place, in that classification. So here it is from the beginning. Chapter 1, valuation. And this is what all of our students here learn at Tandon. It's a required course, it's a core course. And we start with the idea that all of finance boils down to a single transaction. Because at a transaction, something special happens. We have a buyer and a seller meet. And even though we assume they have similar views, they somehow both agree to trade. One buys and one sells. What's the difference? The buyer thinks that the expected return is going to be higher than they can get elsewhere, or what they're required to get naturally from having that investment in another place. The seller doesn't think that the asset's going to do that for him or her. And so he or she takes the opposite position, and the required return is greater than or equal to what the seller expects. So the only way those two things can be true at the same time is if the buyer and seller, if they both transact, these have to be equal. So that's the simplest version of the equation. Required return equals expected return. Now, what are these components? Required return, that's my opportunity cost. That's my time value of money. Because if I have to put up money, I have to make cash for that. And then I have to be compensated for risk. That's my risk compensation. The expected return has two components. When I buy stock, I can't expect to get much out of it except for capital gains and cash flows. That's all we get most of the time. Right? Not counting coupons for discounts on the product and stuff like that. The second comment I make is that we always in this class, we turn returns into dollars, not percentages. And the reason for that is we can't deal with things like short positions, short futures, short options, which have potentially infinite loss. We can't calculate a rate of return on those instruments, and so they wouldn't be able to fit into the integrated theory. So if we use dollars instead of percentages, we can fit everything in. Okay, so we look at a 1 year period or one period. The time value is just what your foregone interest, the risk-free rate. So that's R times the value of the asset. The compensation for risk is the risk measure, which is K. Sorry, the cost of risk is K. The measure of risk is something. I put sigma in there as a placeholder, but there's a cost of risk associated with holding the asset, has to be earned. The capital gain is the expected change in the price of the asset from time 0 to time 1. Everyone knows. And the expected cash flow is just the cash flow. So here it is. Put all these terms together, you get a very simple linear algebraic equation. Now comes the fun part. What can I actually use this for? Okay, let's look at a repeat slide. Why is this GVE so beautiful? We call it the general valuation equation. It's beautiful because it can value both simple and complex cash flow patterns and complex instruments. And that's what I'm going to demonstrate in the next few minutes. The discount rate will assume constant. We could also absorb the risk into the discount rate for the time being. If we valued a cash flow in 1 year, we all know what the present value of that is, right? Cash flow divided by 1 plus R. But if you take apart the components, it's actually a little bit tedious, but you can see combine the time value of R V0, the risk compensation is 0 if it's risk-free. The capital gain, you lose the asset when you get the cash flow, so you get 0. You give up the asset V0, so the capital gain is 0 minus V0. And the cash flow is C1, solve for C1. Everyone hopefully agrees. Now we do a perpetuity. I think most of us of a certain age remember deriving the present value of a perpetuity as the sum of a geometric series. And we derived it, and isn't that neat that it came out so even and so simple? But in fact, in the GVE, it's even simpler. Time value is always RV0, right? The value times 0, and then R is what the return is at to make. There's no risk compensation, there's no capital gain because the profile of the perpetuity stays the same. So the cash flow pattern at time 0 is exactly the same thing we see starting at time 1. So the capital gain has to be 0. Setting it equal to 0, we get immediately in one line, what's the present value of the perpetuity? Growing perpetuity. The same, except when we do the capital gain, we find that when we look at the cash flows from point time 0 and the cash flows from the point of view of time 1, they're higher by a multiple of 1 plus G. So V1 must be, the value time 1 is 1 plus G times the value at time V0. So the capital gain is GV0.
You need G less than R here?
Yeah. Certain details have been swept under the rug. Yeah, this is a primer for kindergartners, okay? I'm just kidding, guys.
because I'll just say in some countries R is negative, so requiring G less than R is actually quite a constraint.
Yeah. Okay, so we got a growing perpetuity. We got annuity. Right, you want to value annuity? If you start out with n payments, in one period you have n minus 1 payments. So your capital gain is you lose the present value of the last payment. Plug it into the equation, boom, you got the annuity pricing formula. Number 5, a growing annuity gets a little messier, works perfectly. Okay, I won't bother you with the algebra. But then I decided to really convince you this has value. Why don't I value some things you haven't valued before? How about a perpetuity that grows in a linear fashion? So it pays $1 in 1 year, $2 in 2 years, $3 in 3 years, and so on. When I look at that in the future, it looks like it starts at 2, then 3, then 4. So the difference in cash flows is always 1. The present value of a sequence of ones is just 1 over R, we know already. So I plug those into the equation. Time value plus 0 is 1 over R plus 1. And the value of this linear perpetuity is 1 plus R over R squared. About a quadratic perpetuity. I have to add a new one every year for the new students so they don't use the past exams. Okay. So for the quadratic perpetuity, which grows with the square of the year, you break it down, right? Time 0 cash flows, time 1, take the difference. It's just increasing by 2. And we can break that into 2 things we already know how to value. Easy as pie. And here, the one for this year on your midterm. Have you ever gone to a finance class and the professor said, what's the present value of the Fibonacci sequence? In your honor, I have Fibonacci's picture in the bottom saying, ¿Qué cosa es questo? So what's the sequence? You know the sequence, right? 1, 1, 2, 3, 5. At time 1, it's going to be 1, 2, 3, 5, 8. Take the difference. It looks just like the Fibonacci series, but it's 1 period delayed. So the present value is V0 divided by 1 plus R. Solve. V0 is 1 plus R over R squared plus R minus 1. And by the way, you need a very high discount rate because, as you know, the Fibonacci series approaches the, what's that called? The harmonic ratio or something? The golden ratio, yeah. So if it's your growth rate, your discount rate has to be bigger than the golden ratio, right? Okay. It wasn't that easy to find a picture of Fibonacci on the internet either. I hope that's him. All right, now the hard part. We did some easy, fun things, right? Let's see if we can really put it to the test. How about the CAPM? The CAPM is a special case of the GVE. If you can see it very clearly, if you multiply all the terms by the value of the asset, so these are all in dollars instead of percentage terms. But if you drop the V's, you see the very well-known CAPM equation.
What's the significance of the I subscript?
Stock I in the CAPM.
Stock I, okay.
Applies for all I. There's some notes here. You don't need to worry about them. This is what we did in class today with our students. With the CAPM not taken from the Sharpe's version of it, but Linder's version of the CAPM. So these for your CAPM aficionados, this is kind of fun because there are different versions that you can use. They're equivalent, but they just approach the problem differently. Sharpe approaches it from the investor point of view. Linder approaches it from the producer point of view. Anyway, long story short, when you do your risk premium, it's proportional to the covariance between the asset and the market portfolio. And so you can write your GVE and that's it. That's the value of the asset in a portfolio, with the covariance used being the risk measure for an asset that's priced that way. Forward contract, a little bit different, because this time it doesn't cost anything to buy a forward contract, right? There's no investment, so RV0 is 0. The risk compensation is the same as if you own the stock. You have to get the same risk because you're transferring the risk to yourself, okay? And then your expected capital gain, of course, is going to be relative to the current forward price and what you think the stock's going to be, where convergence is forced. When you solve this, you get the forward pricing equation. Are you ready for the conclusion? The option. So time value of the option, RC. Risk-free rate times the call option value. Risk compensation, you take the risk premium for the stock, alpha minus R, multiply times the covariance, right, or the delta of that with respect to the stock. It's equal to expected capital gain, which is found by Ito's lemma. And the cash flow, of course, is 0. The alpha terms cancel. As you see, alpha S CS cancels, and so we get risk neutral pricing. So do I win? Is this the most beautiful equation in finance? You like it? All right. You guys know it though. All right. All right, that's all I got. Any questions?
Let's give the speaker a hand.
Thank you.
Thank you very much. All right, so just tell your friends this will be uploaded to YouTube next week, and so if you're listening, you know, review the video. Okay. Thanks.
Just don't send it to Merton. He's going to send me a nasty note.